Okay, so in the last video, we defined the conjugate of a group and the conjugate of an element. Now that we have done that, we can define two and actually four nice things. The first is a normal subgroup, but later on we can also define a normalizer and the centralizer of a group. Okay, so first let's start with a normal subgroup. So normal subgroup N, which is a subgroup of G obviously, G is a big group, is any group such that for all G in G, we have G NG inverse is just equal to N. So we already know what this thing is. It's just this set, right? So for every element in capital N, we take its conjugate with the element small g, and this is a subgroup, right? So this is a subgroup of capital G. So if this subgroup is the same thing as capital N, then what we say is, so we're essentially saying that the conjugate of the whole subgroup N itself, that's the same thing as N. So in that scenario, we say that N is a normal subgroup in G. And so we say N, this right triangle thing, and it could be G itself, so there's a possibility of equality. We put this, yeah. So we just define what a normal subgroup is, right? Okay, next we want to define something that's called a normalizer. So for any random subgroup H of G, let's just consider all the elements such that GH G inverse is H. So it might be that this equation does not hold true for every single G in G, right? So this does not happen, but it could be that it holds true for some elements, right? So the set of elements of G in G such that this happens, this thing is the normalizer of H in the group G. It's written like this: N sub G of H, right? Now similar to this, there's another thing which is called the centralizer. So that's written as sometimes as C sub G, sometimes as Z sub G. I like C personally. I'm going to write it like this. So it's C sub G of H. That's all the elements in G such that for all the elements in capital H, essentially GH G inverse is just H. So it conjugated with G, that's just H, like for every element in H. So another way to think about it is that you can essentially write GH is equal to HG, right? So G and H commute. So basically it's all the elements such that for any element in capital H, the elements commute, right? So if I had to write in words, it's basically like all elements in G such that, so all elements capital G, sorry, small g in capital G, such that for all elements H in H. I know it sounds very funny in words, but I think on the screen it's clear what I'm doing. What's going to happen is that G and H commute, right? So we defined the centralizer. Now with this the other definition of centralizer, we can define another property, so another object. It's called the center of a group, written as Z of G or C of G. I like Z of G sometimes anyway. So it's essentially the centralizer. It should be C over there, not that. It's a centralizer with respect to capital G of the whole group G itself, right? Yeah. So essentially it's the set of all elements in G such that for all other elements, let's say G dash in G, G dash, I shouldn't say G dash, let's use H instead. So for any other element in capital G, what's going to happen is that GH is equal to HG, right? So any two elements commute if one of the elements is in the center of G, right? Or you could say that all the elements commute with everything in the center of G. Yes, it's like there's this pun that, you know, if you are an element, then you want to go to the center, like you commute to the center, and then it doesn't leave you changed essentially, and some weird stuff like that. But never mind all that. Yeah, like everything goes to the center, like all paths lead to something like that. Okay, so that's the center of a group. One thing to notice is that this is a commutative group, like by default, right? So for any two elements h1 h2 in Z of G, since they're also in since h2 is also, this implies like h2 is in capital G and that h1 is in center of G, like obviously, like this is like really obvious. This is obviously true because this is a subgroup of G. But by definition, what this implies is that, you know, h1 h2 is equal to h2 h1, and so for any elements in the center, they commute. So essentially, Z of G is an abelian group or a commutative group. So the operation, whatever binary operation you have, it's commutative for the elements which is in the center. Now this is not the only abelian group, but it is certainly an abelian group, right? Okay, cool. So that was the center of a group. Okay. Yeah, I guess this much is enough for this video. So I'll see you guys in the next video. Bye.